Welcome, curious minds and fellow stargazers, to Dreamy Science, the place where we don't just scratch the surface of knowledge, but dive headfirst into the vast, shimmering ocean of scientific wonder. Here, every discovery is an invitation to marvel, every explanation a journey to the edge of what we thought possible. Today we're going to embark on a mental voyage, one that genuinely stretches the very limits of human imagination, pushing against the comfortable boundaries of our everyday understanding. It's something so unbelievably vast, so profoundly immense, that it almost defies comprehension. Yet, paradoxically, it is the very stage upon which our entire existence plays out, the grand backdrop to every breath we take, every dream we chase, every scientific mystery we unravel. I'm talking, of course, about the sheer, mind-boggling scale of the universe we can actually see. It's a concept that often leaves me speechless, even after countless hours spent pondering its implications. We, as humans, have a natural tendency to simplify, to categorize, to fit the incomprehensible into neat little boxes. So, we often talk about the universe as if it's a single, knowable, perhaps even finite entity, a cosmic bubble we can someday fully map and understand. But the truth, as is so often the case in science, is far more nuanced, infinitely more complex and, dare I say, bewilderingly grander than we typically allow ourselves to imagine. It's a truth that simultaneously humbles and exhilarates me. To truly grasp this, let's try a little thought experiment. Imagine for a moment that you are standing in a perfectly dark, perfectly silent, perfectly empty room. The kind of darkness that presses in on you, so absolute that you can't even discern the shape of your own hand in front of your face. There's no sound, no echo, just an overwhelming sense of isolation. You have nothing but a small, ordinary flashlight clutched in your hand. When you finally muster the courage to click it on, a small, comforting sphere of light blossoms around you. This light travels outwards, cutting through the velvety blackness, revealing the dust motes dancing in its beam, perhaps a rough-hewn wall just a few feet away, or the smooth, cool surface of the floor beneath your feet. But beyond that illuminated sphere, just a few short paces from where you stand, everything remains in profound, impenetrable darkness. You know the room extends further, perhaps infinitely, but your light simply cannot reach it. What lies beyond remains a mystery, forever veiled. Now, I want you to scale that up. Not by a factor of 1,000, or 1,000,000, or even 1,000,000,000. Scale that up by a factor that would make the numbers themselves dizzy. That would leave even the most seasoned mathematician blinking in disbelief. Our flashlight in this cosmic analogy isn't a battery-powered device. It's light itself, the fundamental messenger of the cosmos. And that room, that perfectly dark, perfectly empty space, that's the entire cosmos, the true, unknown expanse of the universe. The speed of light, while incredibly fast, approximately 186,000 miles per second, is still finite. It takes time for light to travel from one point to another. This simple, elegant fact is the key to understanding our cosmic limitation. We can only see as far as light has had time to travel to us since the very beginning of the universe. It's a look-back time, a journey through cosmic history with every photon that reaches our eyes or our telescopes. This isn't just a limit of our current technological prowess, a flaw in our telescopes that future generations might overcome. No, This is a fundamental, inescapable boundary woven into the very fabric of space-time. It's a humbling realization, a stark reminder of our place within an incomprehensibly vast reality. We are in essence trapped within our own cosmic light bubble, our observable universe. The most distant, ancient light we can detect has been travelling for approximately 13.8 billion years. This light isn't from stars or galaxies as we know them today. It's a faint, pervasive glow, an echo from a time when the universe was a mere infant, just 380,000 years old after the fiery crucible of the Big Bang. Imagine that. We are detecting photons that embarked on their journey when our universe was barely out of its primordial cradle. At that epoch, the cosmos was a hot, dense, opaque soup of plasma, far too energetic for atoms to fully form. Light particles, photons, were constantly scattering off free electrons and protons, unable to travel freely. It was like being inside a thick, glowing fog. But as the universe expanded and cooled, a pivotal moment arrived. Roughly 380,000 years after the Big Bang, the temperature dropped sufficiently for electrons and protons to combine, forming the first stable, neutral atoms of hydrogen and helium. This event, known as recombination, had a profound consequence. The universe suddenly became transparent. The photons, previously trapped, were finally free to stream across the cosmos, carrying with them the imprint of that nascent universe. This relic radiation, stretched and cooled by billions of years of cosmic expansion, is what we now detect as the cosmic microwave background, CMB. The oldest light in the universe, a fossilized snapshot of its infancy. It's a faint whisper, a ghostly murmur from the dawn of time, carrying stories of creation. But here's the truly strange part, the twist that often sends a shiver down my spine when I consider it. The objects that emitted that light, those nascent atoms whose photons we detect as the CMB, are not 13.8 billion light-years away. If that were the case, it would be a relatively straightforward calculation. A simple matter of distance equals speed times time. However, the universe is not a static canvas. It is a dynamic, ever-expanding entity, stretching and growing with each passing moment. And that, my friends, makes all the difference. And so, we arrive at a truly mind-bending cosmic conundrum, don't we, my friends? A puzzle that stretches the very fabric of our understanding, challenging the comfortable confines of everyday intuition. We've meticulously established that the cosmic microwave background, that ancient ghostly light, embarked on an epic journey, travelling for an astonishing 13.8 billion years to finally grace our detectors here on Earth. Our logic, that steadfast, grounded, earthly logic we rely on for everything from balancing our checkbooks to launching rockets, would immediately dictate a seemingly undeniable truth. The objects, or rather, the primordial regions of space which emitted that light, must, by all accounts, be precisely 13.8 billion light-years away from us right now. It seems so straightforward, doesn't it? A simple multiplication of speed by time. But I tell you, with a certainty born of cosmic revelation, they are not. They are, in fact, vastly, almost inconceivably further. The thought alone sends a shiver down the spine, a thrilling jolt of intellectual dissonance. How can this possibly be? How can light faithfully travel for a certain immense amount of time, yet the source of that light, the very point from which it sprang forth, is now at a completely different, astronomically greater distance. It feels like a trick, a cosmic sleight of hand designed to humble our human intellect. This, curious minds, is precisely where we delve into one of the most profound and counterintuitive truths of our universe, a truth that asks us to shed our preconceptions and embrace a grander, more dynamic reality, the expansion of space itself. Not objects moving through space, but space growing. Imagine, if you will, a gigantic, warm and wonderfully fragrant cosmic loaf of raisin bread, fresh from the oven, still in its nascent stages. When the baker, perhaps a cosmic entity with flour-dusted hands, first mixes the dough, the raisins are relatively close to each other, scattered throughout the nascent sticky mass. You can pick out individual raisins, observe their proximity, almost touch them. Now, as the bread begins to bake, as the latent yeast awakens and the warmth permeates, the dough starts its miraculous ascent, rising and expanding. Visually, you see the raisins drifting apart, their tiny forms becoming more distant from one another. But here's the crucial insight. The raisins aren't moving through the dough in any active sense. They're not actively swimming or crawling away from each other, exerting their own propulsive force. Instead, it is the dough between them that is stretching, growing, carrying them further and further apart as it swells. From the perspective of any single raisin, every other raisin appears to be moving away, not because the raisins themselves are in motion, but because the very fabric of their existence, the dough, is expanding, relentlessly pushing them outwards. It's a subtle but profound difference. Or picture an inflatable balloon, perhaps a vibrant blue one, taut and smooth. If we take a marker and draw a constellation of small distinct dots on its surface, let's say representing galaxies, and then begin to slowly, steadily inflate it, what happens? The dots, those little ink galaxies, move further and further apart from one another. They haven't travelled across the surface. They haven't slid or rolled. Instead, the surface itself has stretched, increasing the distance between them, carrying them along for the ride. You can almost feel the rubber expanding under your fingertips as you blow air into it, visualizing those dots receding. This, in essence, is what's happening in our universe. But instead of dough or a balloon surface, it's the very fabric of space-time that is expanding. The galaxies, those magnificent islands of stars, the sprawling clusters of galaxies, the ethereal nebulae, they are like the raisins or the dots. They are largely stationary within their local pockets of space, bound by their own gravity, much like a cluster of raisins might stick together in a particularly dense part of the dough, or a few dots might be drawn closely. But the vast stretches of space between these colossal cosmic structures are continuously growing, stretching, and expanding, pushing these celestial entities ever further apart. It's a dynamic, living cosmos, constantly reshaping itself. When those first intrepid photons of the cosmic microwave background were finally freed, breaking away from the dense, opaque plasma that held them captive, 13.8 billion years ago, the universe was a mere infant, only about 380,000 years old. It was an incredibly dense and searingly hot place, a blinding fog of plasma, where light couldn't travel freely for long before being scattered. Everything was much, much closer together, compressed into a smaller volume than we can scarcely imagine. Those early glowing particles, those fundamental building blocks that emitted the CMB, were relatively near to what would eventually become our own cosmic neighbourhood, a mere stone's throw in the grand scheme of things. But from the precise moment those photons began their epic journey towards us, a journey spanning unimaginable eons and distances, the universe has not stood still. Oh no, not for a single instant. It has been expanding relentlessly ever since, like a tireless engine of cosmic growth. So as those photons travelled through the vast cold vacuum of space at the ultimate speed limit, the speed of light, the very space they were traversing, was simultaneously stretching, lengthening beneath them. It's akin to trying to walk across a moving walkway in an airport that's also getting longer beneath your feet with every step you take. You are undeniably moving forward, exerting effort, making progress. But the destination is receding even as you approach it, like a mirage that keeps its distance. It's a race against an ever-growing track. This means that while the light itself has been diligently travelling for 13.8 billion years, covering an immense distance through space-time, the source of that light, the specific region of space from which it originated, has been simultaneously carried away by the expanding fabric of the cosmos. The distance between us and that ancient distant source has been continuously increasing, accumulating over cosmic eons, adding billions upon billions of light years to the gap. It's not just the journey of light, it's the journey of space itself. This, my friends, is the crucial distinction between look-back time and current proper distance. The look-back time is a measure of history. It tells us precisely how long the light has been travelling to reach our eyes, a direct witness to the past. It's the age of the image we perceive. The current proper distance, however, tells us how far away those objects are right now, in this very instant, having been carried along by the relentless, continuous expansion of the universe since they emitted that ancient light. It's the present-day reality of their separation from us. And here, my fellow travellers on this cosmic voyage, is where the numbers truly begin to boggle the mind, to stretch our cognitive limits. If we factor in the universe's expansion rate, a rate that has varied over cosmic history but is now precisely measured over the past 13.8 billion years, we find that those primordial regions that emitted the cosmic microwave background, which were once relatively close in the early compact universe, are today not 13.8 billion light years away. That intuitive number, that simple calculation, is dramatically insufficient. They are, in fact, an astounding, almost incomprehensible 46.5 billion light years distant from us in every direction. The sheer scale is breathtaking, almost disorienting. Let that sink in for a moment. 46.5 billion light years. The number hangs in the air, heavy with implications. That's the true radius of our observable universe, the absolute maximum reach of our cosmic vision. Not the 13.8 billion years that light has been travelling, but 46.5 billion light years, a testament to the power of expanding space. It's a magnificent sphere of cosmic influence, a shimmering bubble of everything we can possibly see, detect, and study, stretching 46.5 billion light years in every direction from our humble vantage point here on Earth. This means the diameter of our cosmic bubble, the distance from one edge of our observable universe to the opposite edge, is a truly staggering 93 billion light years. It's a number that makes our planet, our solar system, even our galaxy, feel utterly minuscule, a speck within an incomprehensibly vast canvas. This immense scale, this mind-boggling expanse, is a direct and unavoidable consequence of the universe's expansion. The light from those most distant regions began its journey when the universe was tiny, compact, and dense, a mere fraction of its current size. But by the time that ancient light, having traversed immense distances and even more immense spans of time, finally reaches us, the space it traversed has stretched so dramatically that its original source is now incredibly, almost unfathomably far away. It's like watching a movie of a distant event only to realize the stage on which it played out has since expanded to a colossal size. This quote, 3, the boundary 46.5 billion light-years out, represents the furthest we can ever see, the ultimate limit of our observational capabilities. It's not a physical wall or an impenetrable edge to the universe itself, which might continue infinitely beyond. Rather, it is simply the limit of how far light has had time to travel to reach us since the Big Bang, precisely accounting for the universe's continuous expansion. Anything beyond that horizon, any light emitted further away, simply hasn't had enough time to bridge the ever-expanding gap between us and its source. It's still out there, travelling, a silent messenger racing across the void, but it hasn't reached our cosmic doorstep yet, and due to the accelerating expansion, much of it never will. It's a poignant thought that there are cosmic stories unfolding that we will never witness. So, while we are absolutely limited by the immutable speed of light, the fastest speed anything can travel through space, the universe's expansion ensures that our observable bubble is far grander, far more ancient, and far more awe-inspiring than a simple multiplication of speed by time would suggest. We are nestled within a sphere of detectability, a magnificent, vibrant tapestry woven from the light of billions upon billions of galaxies, each a universe unto itself, stretching out to 46.5 billion light-years in every direction. A breathtaking panorama of cosmic history. But this, my friends, is just our observable universe. It's our cosmic goldfish bowl, a truly immense one, yes, a bowl of unimaginable proportions, but a bowl nonetheless. It's what we can see, what we can detect with our most powerful telescopes, what we can measure and study from our unique vantage point in space and time. It's our personal window into the cosmos. The profound question that naturally arises, the one that whispers to our deepest curiosity, to the very core of our exploratory spirit, is this: what lies beyond this colossal 93 billion light-year expanse? If our observable universe is merely a bubble, however vast and ancient, however filled with wonders, does that imply there's more, much more outside of it? Does the universe actually have a finite edge, a boundary beyond which there is nothing, or does it continue endlessly, infinitely, into realms we can never perceive, never touch, never even imagine? This, fellow stargazers, is where our journey truly begins to transcend the limits of observation and delve into the realm of theoretical physics, philosophical contemplation, and the very nature of existence itself. We've defined our cosmic bubble. Now let us peer beyond its shimmering, expanding surface and ask, is the universe actually infinite? Welcome back, curious minds and fellow stargazers, to dreamy science. We left off standing at the precipice of our cosmic understanding, gazing out at the magnificent, almost incomprehensible expanse of our observable universe. A bubble of existence stretching 93 billion light-years in diameter. It's a staggering thought, isn't it? But here's the crucial distinction, the very heart of our current quest. This observable universe is not necessarily the entire universe. Imagine for a moment that you are a tiny microscopic creature living on the surface of an enormous, perfectly smooth balloon. From your perspective, you can only see a certain distance across the surface. That's your observable universe. But does the balloon end just beyond your sight? Of course not. The balloon continues, vast and unbroken, far beyond your tiny horizon. Our cosmic horizon, that 93 billion light-year boundary, is a limit imposed by light speed and time, not by the universe itself. It's the furthest light has had time to reach us since the Big Bang. But what about all the space, all the galaxies, all the potential wonders that lie beyond that horizon? The universe, my friends, is almost certainly much larger than what we can currently perceive. In fact, many cosmologists believe it's not just larger, but infinite. The very word, quote, "for," sends a shiver down the spine, doesn't it? It challenges our finite minds, pushing the boundaries of what we can truly grasp. How do we even begin to contemplate something without end, without boundary, without limit? It's like trying to count to the highest number, or walk to the edge of forever. But here's where the universe gets truly fascinating, where science steps in to offer us tantalizing clues. To understand if the universe is infinite, we don't look for an edge, because an infinite universe, by definition, has no edge. Instead, we look at its shape. We examine the very geometry of space itself. Think back to your high school geometry class. Remember Euclidean geometry? The kind where parallel lines never meet, and the angles in a triangle always add up to 180 degrees. That's the geometry of a flat plane. If the universe, on its grandest scale, is like a flat plane, then it would be infinite. Imagine a sheet of paper stretching forever in every direction. That's a flat, infinite universe. But what if the universe isn't flat? What if it's curved? There are two other possibilities, two other cosmic shapes that could define our reality. First, imagine the surface of a giant sphere. If you draw two lines on a sphere, say 2 lines of longitude starting at the equator, they will eventually converge at the poles. The angles in a triangle drawn on a sphere would add up to more than 180 degrees. This is called positive curvature. If our three-dimensional universe has positive curvature, it would be like the surface of a sphere, but in a higher dimension. It would be finite, but it would have no edge. Just as an ant walking on a sphere never finds an edge, but eventually returns to its starting point, so too might a spaceship in a positively curved universe. It's finite in volume, but unbounded. A truly mind-bending concept. Second, consider a saddle shape, or the surface of a Pringle chip. Here, parallel lines would diverge, spreading further and further apart. The angles in a triangle would add up to less than 180 degrees. This is negative curvature. If our universe has negative curvature, it would be infinite, like a hyperbolic plane. It would stretch out forever, constantly flaring outwards, even more dramatically than a flat plane. So, we have three fundamental shapes for the universe: flat, positively curved, or negatively curved. And the answer to quote 6 hinges on which of these shapes our universe actually possesses. How, you ask, do we measure the shape of something as vast and ethereal as the universe itself? We can't exactly take out a giant cosmic tape measure, can we? No, my friends. We turn to the very fabric of space-time and to the echoes of the Big Bang itself. The shape of the universe is intrinsically linked to its total density, the amount of matter and energy packed into every cubic light-year of space. There's a magic number called the critical density. If the universe's actual density is greater than this critical density, it means there's enough stuff to warp space into a positively curved, finite shape. Think of it like a giant gravitational pull that eventually brings everything back in on itself, even if it takes an eternity. If the universe's actual density is less than the critical density, then space is negatively curved and infinite. There isn't enough stuff to pull it back. It just keeps expanding and flaring outwards forever. And if the universe's actual density is exactly equal to the critical density, then space is perfectly flat, and therefore infinite. So, the grand cosmic detective work begins. We need to weigh the universe. And how do we weigh the universe? We look at the most ancient light we can detect, the cosmic microwave background, or CMB. Remember that faint ethereal glow, the quote nines of the universe, emitted when the cosmos was just 380,000 years old? This CMB isn't perfectly uniform. It has tiny temperature fluctuations, slight hot spots and cold spots that represent regions of slightly higher or lower density in the early universe. These are the seeds from which all the galaxies and galaxy clusters eventually grew. These hot and cold spots in the CMB are incredibly important. They act as standard rulers in the sky. We have a very good theoretical understanding of how big these fluctuations should have been at the moment the CMB was emitted. We know their intrinsic size from the physics of the early universe. Now imagine holding up a ruler at arm's length. If the universe were positively curved, it would act like a giant magnifying glass, making those CMB spots appear larger than they actually are. If the universe were negatively curved, it would act like a giant fisheye lens, making the spots appear smaller. But if the universe is flat, those spots should appear exactly the size our physics predicts. This is where incredible missions like NASA's WMAP, Wilkinson Microwave Anisotropy Probe, and the European Space Agency's Planck satellite come in. These spacecraft meticulously map the entire sky, capturing the CMB with unprecedented precision. They analyze those tiny temperature fluctuations, those fossilized ripples in the early universe, and compared their apparent size to their predicted intrinsic size. And the results, my friends, have been astonishingly consistent and clear. Time and time again, the data tells us that those hot and cold spots in the CMB appear exactly the size they should if the universe is flat. This is a profound discovery. It means that the total density of matter and energy in our universe is incredibly close to the critical density. It means that, as far as our most precise measurements can tell, the geometry of the universe is flat. And what does a flat universe imply? It strongly suggests an infinite universe. If space is truly flat, it extends forever in every direction, without boundary, without end. It's a vast, boundless ocean of galaxies, stretching into an eternity we can scarcely fathom. The implications are staggering. If the universe is infinite, then everything that can happen will happen, somewhere, an infinite number of times. There might be infinite copies of you, reading infinite copies of this very chapter, in infinite universes just like ours. It's a dizzying thought, a cosmic mirror reflecting endless possibilities. However, a crucial caveat, my friends, because science is always about precision and humility in the face of the unknown. While our measurements show the observable universe to be incredibly flat, we are only measuring our observable universe. It's possible that the entire universe could be so incredibly vast, so unimaginably huge, that our observable portion is merely a tiny flat patch within a much larger, subtly curved structure. Think of it like being on the surface of the Earth. From your immediate perspective, the ground beneath your feet appears perfectly flat. You can't perceive the Earth's curvature unless you travel great distances or observe it from space. Similarly, our observable universe might be too small a sample to detect a very gentle, large-scale curvature if the entire universe is truly gargantuan, or even finite but much, much larger than our horizon. This leads us to the realm of cosmic topology, the overall connectivity and global structure of the universe. Even if the universe is flat, it doesn't necessarily mean it's topologically infinite in the simplest sense. It could be finite but unbounded, like a giant three-dimensional donut, a torus. If you travel far enough in a universe with this topology, you would eventually loop back to where you started, without ever hitting an edge. We haven't detected any such wraparound effects, which would manifest as repeating patterns in the CMB, or repeating clusters of galaxies. If such a loop exists, it must be larger than our observable universe. So, while the evidence for a flat universe is compelling, strongly pointing towards spatial infinitude, the absolute proof of infinity remains just beyond our grasp. The universe is, at the very least, far, far larger than our observable bubble, and given its flatness, it is highly probable that it truly extends without limit. We stand at the precipice of this understanding, humbled and exhilarated. The universe, in its boundless majesty, continues to surprise and challenge us. Is it infinite? All signs from the whispers of the Big Bang point to a resounding yes. But the true nature of its endlessness, the profound implications of such an existence, continue to fuel our deepest scientific and philosophical inquiries. Next time, my friends, we will delve into another mind-bending possibility. If our universe is just one of many, perhaps even an infinite number of universes, prepare yourselves for a journey into the multiverse. Welcome back, my friends, my fellow stargazers and cosmic cartographers. We just scratched the surface of our own universe, didn't we? We peered into its vastness, its apparent flatness, and wrestled with the mind-bending idea that our observable cosmos, while immense beyond comprehension, might only be a fraction of a far grander, perhaps infinite whole. We contemplated the tantalizing possibility that even a flat universe could loop back on itself, a cosmic Mobius strip, though no telltale patterns have yet graced our telescopes. But what if the profound questions about our universe's ultimate extent and uniqueness are just the beginning? What if the very definition of universe needs to expand? What if our grand cosmos, with its billions upon billions of galaxies, its intricate laws, its delicate balance that allows for stars and planets and us, What if this magnificent tapestry isn't the only show in town? What if it's merely one thread, one vibrant hue, in an unimaginably larger, more complex fabric? Tonight, curious minds, we embark on a journey that pushes the boundaries of our imagination even further, into a realm where the concept of infinity takes on a dazzling, dizzying new form. We're talking about the multiverse. For many, the multiverse conjures images from science fiction, parallel dimensions, alternate realities where you made a different choice, where dinosaurs still roam, or where pigs really do fly. And while fiction often sparks our deepest scientific inquiries, the multiverse is far more than just a playful thought experiment. It's a serious, albeit highly speculative concept woven into the very fabric of several leading theories in theoretical physics, cosmology, and quantum mechanics. It's a proposed solution to some of the most perplexing puzzles about our existence and the nature of reality itself. So, what is a multiverse? Simply put, it's a hypothetical collection of multiple universes, each potentially with its own unique set of physical laws, constants, and initial conditions. It's an ensemble, a cosmic choir where our universe is just one voice, perhaps singing its own unique tune. Let's dive into some of the most compelling and sometimes bewildering flavors of this cosmic ensemble. Imagine for a moment that our universe is truly infinite. We explored this possibility last time, didn't we? If space extends forever, and if matter and energy are distributed even somewhat uniformly throughout this boundless expanse, then the implications are truly staggering. This leads us to the first and perhaps most intuitive type of multiverse. Level Y, the infinite space multiverse. Think about it. In an infinite universe, there are only a finite number of ways that particles can arrange themselves within any given finite volume. If you have an infinite number of such volumes, then eventually, by sheer statistical probability, patterns must repeat. It's like shuffling a deck of cards an infinite number of times. Eventually, you're going to get the exact same sequence of cards again, and again, and again. This means that far, far beyond our cosmic horizon, the 46.5 billion light-year boundary that limits what we can ever see, there could be other regions of space identical to ours, other Earths, other yous, reading this very sentence, contemplating this very thought, or perhaps slightly different versions. A you who chose coffee instead of tea this morning. A you who lives in a world where gravity is a tiny bit stronger, or where the dinosaurs never went extinct. These aren't alternate timelines in a mystical sense. They are simply other regions of space so incredibly far away that their light will never reach us, yet statistically destined to exist in an infinite universe. It's a dizzying thought, isn't it? That your doppelganger might be out there living a subtly different or even identical life, simply because the universe is so vast, so truly infinite, that all possibilities allowed by physics must eventually play out. But what if infinity isn't just about repeating possibilities, but about creating entirely new ones? This brings us to a more dynamic and perhaps even more mind-boggling concept. Level 2, the bubble universe or inflationary multiverse. Remember our discussion of cosmic inflation, that incredibly rapid expansion of the universe in its earliest moments, which smoothed out space and planted the seeds for galaxies. Well, some theories suggest that inflation, once it starts, might never fully stop. Instead, it might be eternal, continuously generating new pockets of space. Imagine a vast, ever-expanding ocean of inflationary energy, constantly bubbling and frothing. Every now and then, in random locations, a bubble of inflation stops, creating a distinct pocket of space. Each of these bubbles then expands and evolves into a full-fledged universe, much like our own. Our universe, then, would simply be one such bubble, floating in an infinitely larger sea of other bubble universes. And here's the kicker. Because these bubbles form independently, the conditions within them could vary wildly. The fundamental physical constants, the strength of gravity, the charge of an electron, the mass of a proton, could be different in each bubble. The number of spatial dimensions might even vary. This offers a compelling explanation for why our universe seems so exquisitely, quote, 15 for life. If there are countless universes out there, each with different laws, then it's no surprise that we find ourselves in one where the laws happen to be just right for stars to form, for carbon chemistry to flourish, and for intelligent beings to emerge and ponder the cosmos. It's not a miracle, it's a selection effect, a cosmic lottery where only the winning tickets produce observers. Now let's take a truly radical leap, one that challenges our very understanding of observation and reality itself. Level 3. The many worlds interpretation of quantum mechanics. This type of multiverse doesn't arise from vast distances or cosmic inflation, but from the perplexing realm of the very small, the quantum world. In quantum mechanics, particles don't have definite properties until they are observed. Instead, they exist in a superposition of all possible states simultaneously. Think of Schrödinger's infamous cat, both alive and dead at the same time until the box is opened. The many worlds interpretation, MWI, proposed by Hugh Everett III in 1957, suggests that when an observation is made, the universe doesn't choose one outcome and collapse the others. Instead, the universe splits. Every time a quantum event has multiple possible outcomes, the universe branches into separate non-interacting realities, one for each outcome. Imagine it. You toss a coin. In one universe, it lands heads. In another, equally real universe, it lands tails. You make a choice, left or right. In this universe, you went left. But in another, a distinct universe branched off at that precise moment, and that you went right. Every quantum interaction, every subatomic flicker, every decision, however small, potentially creates new universes. This isn't just about different cosmic constants. It's about every conceivable possibility being realized in some branch of this ever-splitting cosmic tree. The other you isn't just far away, they're in an entirely separate, inaccessible reality, a consequence of a different quantum measurement. It's a mind-bending idea, suggesting an infinite number of parallel realities constantly being created, utterly inaccessible to one another, yet all equally real. And finally, for the truly intrepid, we venture into the most abstract and perhaps most profound type of multiverse. Level 4, the mathematical universe hypothesis. This radical idea, championed by physicist Max Tegmark, suggests that mathematics isn't just a description of the universe, it is the universe. That is, our physical reality is simply one particular mathematical structure, and all mathematically consistent structures exist as universes. Every possible set of mathematical equations, every consistent abstract framework, corresponds to its own reality. If this is true, then our universe, with its specific laws and constants, is just one instance of a mathematical pattern. Other mathematical patterns, other equations, other structures represent other universes, some perhaps so alien that they defy our current human imagination. This multiverse is not about space, or bubbles, or quantum splits, but about the fundamental nature of existence being inherently mathematical. It posits that there is no external reality to describe. The mathematical structure is the reality. So, where does this leave us, my friends, when we stand on the precipice of such boundless possibilities? The multiverse, in its various guises, offers tantalizing answers to some of our deepest questions. It elegantly addresses the fine-tuning problem with the anthropic principle. If everything that can happen does happen across an infinite ensemble of universes, then it's no surprise we find ourselves in one where life is possible. Yet, it also presents profound challenges. The biggest one, of course, is testability. How do we prove the existence of other universes if, by their very nature, they are often beyond our ability to observe or interact with them? For now, many multiverse theories remain within the realm of theoretical physics, elegant mathematical constructs that offer compelling explanations but lack direct empirical evidence. Are there subtle clues in the cosmic microwave background, perhaps signs of collisions with other bubble universes? Can we find unique quantum phenomena that hint at branching realities? These are questions that continue to drive fierce debate and cutting-edge research. The multiverse, whether a vast expanse of repeating realities, an ocean of bubbling cosmos, an ever-splitting quantum tree, or a tapestry of mathematical structures, forces us to confront the limits of our understanding. It pushes us beyond the comfortable confines of quote 20 and invites us to consider a cosmos so grand, so infinitely varied, that our own existence might be just one tiny unique note in an eternal symphonic whole. Is the universe actually infinite? Perhaps it's not just a universe we should be asking about, but the entire, immeasurable, incomprehensible multiverse itself. The journey, my friends, continues, and the wonder, I promise you, only grows. Welcome back, curious minds and fellow stargazers, to our cosmic journey on dreamy science. We've plunged into the dizzying depths of the observable universe, navigated the perplexing geometry of space, and even dared to peer beyond the veil of our own reality into the realm of the multiverse. We've touched upon concepts so grand, so utterly mind-bending, that they challenge the very foundations of our understanding. Last time we left off pondering the tantalizing yet frustrating nature of the multiverse. We explored its various theoretical flavors, from the infinite repetitions of level 1 to the bubbling cosmic foam of level 2, the quantum splits of level 3, and the pure mathematical forms of level 4. Each offers a compelling, albeit speculative, answer to some of the universe's most profound questions, like why our cosmos seems so perfectly fine-tuned for life. But, as we concluded, the elephant in the cosmic room remains. How do we know? How do we test these colossal hypotheses? How do we gather evidence for something that, by its very definition, might lie beyond the reach of our telescopes, our detectors, our very senses? This, my friends, is the cutting edge of cosmology, where the lines between physics, philosophy, and pure imagination blur. This is where science grapples with its ultimate challenge, exploring the untestable, or perhaps the currently untestable. Imagine, if you will, being an ant on a vast, intricately patterned rug. You can explore your immediate vicinity, map the threads, understand the local geometry. But how do you know if your rug is just one of many identical rugs stretching infinitely across a floor, or if it's merely a small patch on a much larger, subtly curved tapestry that eventually loops back on itself? And what if, just beyond the edge of your rug, there are other rugs made of entirely different materials, woven with alien patterns, existing in dimensions you can't even perceive? This, in essence, is our predicament with the multiverse. So how do we, the cosmic ants, even begin to search for echoes from beyond our rug? The answer lies in looking for subtle signatures, faint whispers that might leak through from these other realities. It's like searching for ripples on a pond caused by a stone thrown far, far away, beyond our direct line of sight. One of the most exciting and highly speculative avenues of research involves scrutinizing the cosmic microwave background, that ancient fossilized light from the early universe that we discussed earlier. Remember, the CMB is our oldest baby picture of the universe, a snapshot of its infant state. It's remarkably uniform, a testament to the smoothness of the early cosmos. But like any good photograph, it has its subtle blemishes, its tiny temperature fluctuations. What if, some cosmologists ponder, one of those tiny, seemingly random fluctuations isn't so random after all? What if a particular quote 22 or quote 23, a peculiar asymmetry in the CMB map, is not just a statistical anomaly, but rather the bruise left by a collision with another bubble universe? Picture two cosmic bubbles, expanding rapidly, brushing against each other in the vast ocean of the multiverse. Such an encounter, however brief, might leave an imprint. A unique quote 24 on the fabric of our own universe that would be observable in the CMB. Scientists are actively searching for these non-Gaussian anomalies, these patterns that defy the expected randomness in the incredibly precise data from missions like Planck. It's an incredibly long shot, a needle in a cosmic haystack, but the payoff, direct evidence of another universe, would be immeasurable. Another fascinating, albeit even more theoretical possibility comes from the realm of brain cosmology. This is where the universe gets truly wild, postulating the existence of extra-spatial dimensions beyond the three we perceive. Imagine our universe as a brain, a sort of cosmic membrane, floating within a higher dimensional bulk. In this scenario, other universes could be other brains, existing very close to us in these hidden dimensions, much like pages in a book. While we can't directly see these other brains, they could exert a gravitational influence on our own. Gravity, being a force that can quote 27 into higher dimensions, might be the messenger. If we could detect minute, inexplicable deviations in gravity at certain scales, or perhaps even find traces of gravitational waves from sources that don't seem to originate within our own visible universe, it could hint at the presence of these neighbouring brain worlds. It's a concept that requires us to completely rethink the very structure of space-time, but it offers a potential pathway for inter-universal interaction. Then there's the mind-bending possibility tied to level 2 multiverse theories, where different bubble universes might possess different fundamental physical constants. What if, at the very edges of our own observable universe, where our cosmic bubble might be thinning or interacting with another, we could detect subtle variations in constants like the speed of light or the strength of gravity, or the mass of an electron. This would be a radical departure from our current understanding, which assumes these constants are, well, constant throughout our universe. Such a discovery would be revolutionary, suggesting a transition zone, a boundary where the rules of physics begin to change, hinting at an adjacent reality governed by a different cosmic code. This is currently beyond our observational capabilities, but the very thought ignites the imagination. And what of level 3? The many worlds interpretation of quantum mechanics. This is arguably the hardest to test directly, precisely because it posits that these branching universes, created with every quantum choice, are non-interacting. Once a universe splits, it's gone, separate, forever beyond our reach. There's no quote 28 quote no quote 29 quote no quote 30 quote from your alternate self who chose the other coffee flavour this morning. Yet the implications are profound. If true, it means that every possible outcome of every quantum event actually happens in some parallel reality. The infinite possibilities aren't just theoretical, they're real, unfolding moment by moment in a ceaseless cascade of cosmic branching. It transforms the concept of infinity from mere endlessness into an endless proliferation of actualized realities. The philosophical implications of these multiverse theories are equally staggering. If our universe is just one of countless others, does it diminish our significance, making us a mere speck in an unimaginably vast tapestry? Or does it amplify the wonder, suggesting an ultimate richness of existence that far surpasses our wildest dreams? The idea that everything that can happen does happen somewhere in some universe is both liberating and terrifying. It offers a potential answer to the quote 31 problem, the observation that our universe's physical constants seem perfectly calibrated for life. If there are infinite universes with varying constants, then it's not surprising that one of them would have the right conditions for life to emerge. It's like winning the cosmic lottery, but in a multiverse, every possible ticket is bought, so someone, somewhere, is guaranteed to win. But this also raises deeper questions. Does the multiverse simply push the question to a higher level? If there's a multiverse generator, what created it? And if there are infinite universes, does that mean every possible permutation of events, however absurd or improbable, must exist? An infinite universe, or an infinite collection of universes, implies that somewhere, out there, there's a universe where a purple, sentient teacup is currently giving a lecture on quantum gravity to an audience of highly evolved bananas. While amusing, such thought experiments highlight the sheer, dizzying scale of what quote 33 truly entails when applied to reality. Ultimately, my friends, the multiverse hypothesis remains firmly in the realm of theory. The lack of direct empirical evidence is its most significant hurdle. Yet the scientific pursuit continues. We design new experiments, build more sensitive telescopes, refine our theoretical models, always pushing the boundaries of what is knowable. We are driven by an insatiable curiosity, a primal urge to understand our place in the cosmos, to grasp the true nature and extent of reality. Is the universe actually infinite? Our journey through the observable universe and its flat geometry strongly suggests a spatially infinite cosmos, at least within our own bubble. But the multiverse concept takes us further, suggesting an infinite collection of universes, each potentially infinite in its own right, or finite but unbounded? The answer, it seems, might be a resounding yes, in ways that are far more complex and profound than we initially imagined. We stand at a precipice of understanding, gazing into an abyss of possibilities. The universe, in its boundless majesty, continues to humble and inspire us. It beckons us forward into the unknown, urging us to question, to explore, to dream. And as long as there are mysteries to unravel, as long as there are echoes to chase from beyond the edge of our known reality, the human spirit of inquiry will continue its relentless, awe-filled quest. The journey, my friends, is far from over. The universe, in all its infinite glory, awaits our continued exploration. Welcome back, curious minds and fellow stargazers, to another mental voyage on dreamy science. We've journeyed far, haven't we? From the edges of our observable universe, a sphere of cosmic light 93 billion light-years across, to the mind-bending implications of a spatially flat cosmos which whispers of infinitude. We've even dared to peer into the theoretical realms of the multiverse, where countless realities might blossom like bubbles in an eternal foam. But here's the thing, my friends. While we've pushed the boundaries of what we can measure and theorize, the ultimate question, is the universe actually infinite, remains a profound, dazzling enigma. We stand at the precipice of human understanding, gazing into an abyss that is not empty, but overflowing with possibilities, each more astonishing than the last. And as we stand here, the implications of what we've discussed begin to truly settle, not just as scientific concepts, but as reflections on our very existence. Consider, if you will, the Level-1 multiverse, the simplest, yet perhaps most unsettling of its kind. The implication of an infinite universe where matter is distributed with a statistical uniformity. If space stretches on forever, and there are only a finite number of ways particles can arrange themselves within any given finite volume, then by the sheer relentless logic of probability, everything must eventually repeat. Not just once, but infinitely many times. Think about that for a moment. It means that somewhere, unimaginably far away in that boundless cosmic expanse, there exists another Earth, and on that Earth there lives another you. Perhaps an exact duplicate down to the very atoms that compose your being, reading this exact sentence at this exact moment. And beyond that, another and another, an infinite parade of yous, your memories, your experiences, your triumphs and your regrets, playing out across the cosmic stage. Is that a comforting thought, my friends? Or is it profoundly unsettling? It challenges our most deeply held notions of individuality, of uniqueness. We cherish the idea that we are singular, that our lives are a unique narrative unfolding in time. But if there are infinite copies of us, living out every conceivable variation of our lives, some infinitesimally different, some vastly so, what then of our free will? Is it merely one iteration among an infinite set of predetermined outcomes? This isn't just science fiction. It's a direct logical consequence of a truly infinite universe. It's the universe itself presenting us with the ultimate cosmic doppelganger paradox, forcing us to confront the very nature of identity in a boundless reality. It's like shuffling an infinite deck of cards. Eventually, every possible sequence must appear and then appear again and again. Now let's cast our minds back to the Level-2 multiverse, the quote 34 spawned by eternal inflation. Here, the implications shift from questions of identity to questions of destiny and design. We marvel at the exquisite quote 35 of our universe, don't we? The fundamental constants, the strength of gravity, the charge of an electron, the mass of a proton, seem perfectly calibrated to allow for the formation of stars, galaxies, and ultimately life. If the strong nuclear force were just a fraction weaker, no stable atomic nuclei would form. If it were slightly stronger, hydrogen wouldn't fuse, and there would be no stars. It's like finding a perfectly balanced pen on its tip, suspended against all odds. For a long time, this fine-tuning presented a profound mystery, leading some to ponder a benevolent designer. But the Level 2 multiverse offers a different statistical explanation. If eternal inflation is constantly churning out an infinite number of bubble universes, each with its own randomly assigned set of physical laws and constants, then it's no longer a miracle that our universe happens to possess the precise conditions for life. It becomes, instead, an inevitability. Think of it this way. Imagine an infinite number of lottery tickets being printed, each with a different combination. The fact that one of them is a winner isn't surprising. The surprise would be if none of them were. We, the conscious observers, simply must find ourselves in one of the universes that allowed for our existence. We are the lucky winners, but only because the cosmic lottery had played an infinite number of times. The anthropic principle, as it's called, takes on a whole new, less mystical dimension when viewed through the lens of the multiverse. It's not about special design, it's about statistical selection. We are like fish in the ocean, naturally adapted to water, and we observe that our universe is perfectly, quote, 36, quote, for us. But we cannot perceive the countless other universes that might be, quote, 37, quote, or quote, 38, quote, or quote, 39, quote, utterly inhospitable to our form of life. These concepts, the infinite repetitions of self, the statistical inevitability of our fine-tuned existence, they challenge our core assumptions about reality itself. If reality is so vast, so varied, so utterly beyond our direct perception, then what does, quote, 40 truly mean for these other realms? Our definition of reality is inherently tied to what we can observe, what we can interact with, what we can measure. The universe, or perhaps the multiverse, might be infinite in ways that transcend our current sensory and scientific grasp, forcing us to confront the humbling truth that our current tools and theories are but a tiny flashlight beam in an incomprehensibly vast darkness. Is the universe actually infinite, or is our concept of infinity merely a reflection of our limited capacity to comprehend something so utterly boundless? So, where do we go from here, my friends? How do we push the boundaries of this profound quest? The empirical evidence for the multiverse remains elusive, as we discussed, but the pursuit continues with unwavering passion. Scientists are developing new generations of instruments, each more sensitive, more precise, designed to peer further back in time, to listen for the faintest echoes of cosmic origins. Consider the future of gravitational wave astronomy. Missions like LISA, the Laser Interferometer Space Antenna, are designed to detect gravitational waves from the very early universe. Waves that are ripples in space-time itself, potentially carrying information from moments before the cosmic microwave background formed. Could these primordial gravitational waves hold a subtle signature, a harmonic distortion, a faint whisper from a collision with another bubble universe? Could they reveal the texture of space-time itself, hinting at higher dimensions or the underlying 41 quote from which all universes emerge? We are learning to listen to the universe in entirely new ways, not just with light, but with the very vibrations of reality. Then there are the theoretical frontiers, where physicists are striving to unify gravity with quantum mechanics, to forge a 42 string theory. Comma loop quantum gravity and other quantum gravity theories are attempting to describe the fundamental nature of space-time at its smallest scales. Perhaps within these elegant mathematical frameworks lie the keys to understanding how universes are born, how they interact, or even how they might be connected through unseen dimensions. These theories, while incredibly abstract, offer potential roadmaps to a deeper understanding of the cosmic architecture, a map that might, one day, chart the vast, intricate landscape of the multiverse. And the search for those cosmic, 43 year in the CMB continues with ever-increasing precision. Future generations of CMB telescopes, perhaps orbiting far beyond Earth's interference, could detect even more subtle anomalies, tiny temperature variations or polarization patterns that might be the fingerprint of an encounter with another cosmic bubble. We are like cosmic detectives, meticulously sifting through the oldest light in the universe for clues, for irregularities, for anything that deviates from the perfect smooth tapestry of our own cosmic bubble. Ultimately, my friends, the question of infinity is not a problem to be solved and then set aside. It is a profound, ongoing journey of discovery that reshapes our understanding of ourselves, our place in the cosmos, and the very nature of existence. It inspires a deep sense of wonder, a humbling recognition of our smallness, and an exhilarating thirst for knowledge. The universe, in its boundless mystery, continues to challenge us, to expand our minds, and to remind us that the greatest adventures lie at the very edge of what we can conceive. Perhaps the real infinity isn't just out there, in the boundless expanse of space or the endless parade of universes. Perhaps it is also within us, in the endless human quest for understanding, in our insatiable curiosity, and in our capacity to dream of what lies beyond the horizon, forever pushing the boundaries of the known into the magnificent unknown. The journey, my friends, is eternal, and so, perhaps, is the truth we seek. Welcome back, curious minds and fellow stargazers, to quote 44. We've journeyed through the astounding scale of our observable universe, peered into the very fabric of space and time, and even dared to glimpse the mind-bending possibilities of the multiverse. We've grappled with the profound implications of a cosmos that might be truly infinite, a concept that stretches the very limits of our imagination. But our quest, my friends, is far from over. The question of infinity, you see, isn't a single monolithic puzzle piece. It's a vast, intricate mosaic, each piece revealing a new facet of the boundless. Last time, we touched upon the ongoing journey, the relentless human spirit of inquiry that propels us to ask these grand questions. Today we dive deeper into how we continue this journey, exploring the frontiers of scientific thought and the tantalizing, often frustrating search for answers at the very edge of our knowledge. The infinity we've mostly discussed has been spatial, an endless expanse of stars and galaxies stretching on forever. But what about time? Is the universe also infinite in its temporal dimension? Does it stretch backward into an eternal past and forward into an endless future? Or is there a beginning, a singular cosmic dawn, and perhaps an ultimate twilight? The Big Bang Theory provides us with a powerful model for the universe's beginning, a moment of extraordinary density and heat from which everything we know emerged. But what preceded the Big Bang? Was there truly nothing? Or was our universe born from a larger, perhaps eternal process? Another bubble in the inflationary multiverse, perhaps, or a cyclical cosmos that collapses and rebounds infinitely? This brings us to one of the deepest chasms in modern physics, the disconnect between general relativity, our exquisite theory of the very large, and quantum mechanics, our equally powerful description of the infinitesimally small. General relativity, with its elegant equations, describes gravity as the curvature of space-time. It works beautifully on cosmic scales, predicting the orbits of planets, the bending of light by massive objects, and the expansion of the universe. But when we try to apply it to the extreme conditions of the Big Bang's first moments, or the heart of a black hole, it breaks down, predicting singularities, points where density and curvature become infinite, infinity again. But this isn't a comfortable, expansive infinity. It's a mathematical red flag, a signal that our theory has reached its limits. On the other hand, quantum mechanics, the realm of the subatomic, tells us that energy, momentum, and even space itself might not be infinitely divisible. They might come in discrete, tiny packets, or quanta. Imagine trying to paint a masterpiece with only the broadest brushstrokes, and then trying to describe the intricate details of a single atom with those same brushes. It just doesn't work. We need a new brush, a new language, to speak of the universe at these extreme intersections. This, my friends, is where the quest for a theory of everything, a unified theory that reconciles general relativity and quantum mechanics, becomes not just an academic pursuit, but a profound philosophical necessity in our search for infinity. Two leading contenders in this intellectual arena are string theory and loop quantum gravity, each offering a radically different vision of reality's fundamental nature. String theory, in its most elegant form, posits that the fundamental particles we observe, electrons, quarks, photons, aren't point-like objects at all, but rather tiny vibrating strings of energy, unimaginably small, far smaller than anything we can currently probe. Different vibration patterns of these strings give rise to different particles, much like different notes on a violin string. But here's the kicker. For string theory to work mathematically, it requires the existence of extraspatial dimensions, perhaps as many as 10 or 11, curled up so tightly that we don't perceive them in our everyday three-dimensional world. Now, imagine that. Our universe, which we perceive as a vast three-dimensional canvas, might actually be a mere slice, a quote 46 floating within a higher dimensional space. If these extra dimensions exist, are they infinite? Could they contain other brains, other universes, perhaps even an infinite number of them, each with its own set of vibrating strings and unique physical laws? This pushes the Level 2 multiverse concept to an even grander, more abstract scale, where infinity isn't just about endless bubbles, but about endless dimensions and possibilities within those dimensions. It's like realizing your flat drawing isn't just one picture, but one page in an infinite book, each page a universe, and the book itself existing in a library of infinite dimensions. Then there's loop quantum gravity, which takes a different approach. Instead of adding dimensions, it tries to quantize space-time itself. Imagine space-time not as a smooth, continuous fabric, but as a woven tapestry made of incredibly tiny, discrete loops, or quote 47 quote of space. If space and time are fundamentally granular, if there's a smallest possible unit of length and a smallest possible unit of time, does that put a finite limit on the universe's fundamental structure, even if it's spatially infinite? It's a bit like saying a digital image can be infinitely large, but is still composed of a finite number of pixels per given area. This theory suggests that at the very heart of a black hole, or at the moment of the Big Bang, there isn't an infinite singularity, but rather a compressed, extremely dense state where space-time loops are tightly interwoven, potentially even bouncing into a new universe. This concept, known as the Big Bounce, offers an alternative to the Big Bang's singularity, suggesting an infinite cycle of cosmic expansion and contraction rather than a single beginning. Infinity, in this view, becomes a temporal loop, a cosmic dance without end. But let's consider another profound aspect of reality: information. Is information the very data that describes every particle, every interaction, every thought, infinite? This question takes us into the mind-bending realm of black holes and the holographic principle. When something falls into a black hole, does the information about its constituent particles truly vanish from our universe? For a long time, physicists debated this information paradox. Stephen Hawking famously suggested that black holes emit Hawking radiation and eventually evaporate, but initially thought the information was lost. However, the consensus now leans towards information being conserved, not destroyed. How can information escape a black hole if nothing can? This is where the holographic principle comes in. Imagine, if you will, that all the information contained within a three-dimensional volume of space, like our entire universe, could actually be encoded on a two-dimensional surface, its boundary. It's like a cosmic hologram, where the detailed 3D image we perceive is projected from a 2D information sheet. Think of a credit card. It looks 3D, but all the information needed to create that illusion is on a flat surface. If the holographic principle holds true for the universe, it suggests that even an infinite spatial expanse might have a finite amount of fundamental information content per given area, or perhaps that the description of an infinite universe can be contained within a finite boundary. This doesn't necessarily mean the universe is finite, but it profoundly changes how we might conceptualize its infinitude, suggesting a deep connection between geometry, information, and the very nature of reality. It's a beautiful, bewildering thought, a vast, seemingly boundless cosmos potentially describable by a cosmic bitmap on a far-off horizon. So where does this leave us, my friends, in our pursuit of infinity? We are at the precipice of understanding, armed with increasingly sophisticated tools and theories. Gravitational wave observatories like LISA, Laser Interferometer Space Antenna, destined for space, promise to detect ripples in space-time from the earliest moments of the universe, or perhaps even from collisions with other bubble universes. These are the subtle signatures. We discussed the cosmic bruises that could provide empirical evidence for a level 2 multiverse. Future CMB telescopes, with even greater precision than Planck, will continue to scan the cosmic background radiation for any anomalies any faint whispers from beyond our observable horizon. But even with these advancements, there remains an inherent, perhaps insurmountable, barrier: our own finite nature. We are finite beings, bound by the speed of light, limited by the lifespan of our universe, constrained by the very architecture of our brains. Can a finite mind truly comprehend the infinite? Can we ever prove infinity, or will it always remain a horizon we endlessly approach but never reach? This journey into infinity isn't just about physics and cosmology. It's a profound journey into ourselves. It challenges our very notions of uniqueness, purpose, and significance. If there are infinite copies of us out there, living out every conceivable variation of our lives, what does that mean for this moment, this consciousness, this particular path we are on? Does it diminish our individuality, or does it amplify the sheer, improbable wonder of this specific instantiation of existence? The answer, I believe, lies in the journey itself. The pursuit of infinity, the grappling with the boundless, is what expands our minds, what fuels our creativity, what humbles us before the incomprehensible grandeur of existence. It reminds us that our universe, whether finite or infinite, is a place of endless mystery and profound beauty, and perhaps, just perhaps, the true infinity we seek is not just out there, in the vast, shimmering darkness, but also right here, within the boundless capacity of the human spirit to question, to explore, and to dream. Until next time, keep looking up, keep wondering, and keep dreaming, for the universe, in all its perplexing glory, awaits our unending curiosity. We've journeyed through mind-bending concepts, my friends, from the cosmic tapestry woven by the Big Bang to the dizzying possibilities of the multiverse, and even to the holographic principle, which suggests our reality might be encoded on a distant boundary, transforming our understanding of information itself within this grand cosmic theatre. Each step has been a revelation, a peeling back of another layer of the universe's infinite onion. But even as these theories offer dazzling new perspectives, they only deepen the central, almost sacred question that began our quest. Is the universe actually infinite? The truth, as we stand here gazing into the profound cosmic abyss, is that we still don't know for certain. We have powerful theoretical arguments, compelling observational data, and elegant mathematical models that strongly suggest infinity, particularly in its spatial dimension. The flat geometry of our observable universe, confirmed by the Planck and Dual-Map missions, is perhaps the most persuasive piece of evidence we possess, an echoing whisper from the early universe that hints at a boundless expanse. But a whisper, however clear, is not a shout of absolute proof. How do you prove infinity, my friends? Can you measure something without bounds? Can you observe the end of something that has no end? It's a profound methodological challenge, isn't it? Our instruments, however sophisticated, are finite. Our observable universe, however vast, is finite. We are, by definition, confined within our cosmic horizon, limited by the speed of light and the finite age of the universe. It's like trying to prove the ocean is infinite by only observing the ripples on the shore. We can infer its vastness, its continuity, its seemingly endless horizon, but we can never truly see all of it. This inherent limitation forces us to rely on inference, on extrapolation, on the internal consistency of our most robust theories. If the universe is truly infinite, it means that beyond our cosmic horizon, beyond that 93 billion light-year diameter bubble we call home, Space simply continues. It doesn't curve back on itself. It doesn't meet a boundary. It simply is. And if it continues indefinitely, then the conditions for level 1 of the multiverse, the repetition of all possible arrangements of matter, become not just plausible, but statistically inevitable. Consider the weight of that implication, fellow stargazers. If the universe is infinite, then somewhere, impossibly far away but undeniably present, there is another Earth, another you, another me, hosting another, quote, 54 episode, perhaps asking the very same questions. And not just one, but an infinite number of them, each playing out every conceivable variation of our lives. It's a thought that simultaneously humbles and bewilders, doesn't it? It challenges our deepest held notions of individuality, of uniqueness, of the precious singular journey we believe ourselves to be on. Does it diminish our existence, knowing that infinite copies of us might exist? Or does it perhaps amplify the sheer, improbable miracle of this specific moment, this specific consciousness, this specific constellation of atoms and experiences that makes I find myself leaning towards the latter. The very fact that we are here, contemplating such boundless possibilities, is a testament to the universe's capacity for wonder, regardless of how many times it might repeat itself across an endless expanse. Our consciousness, our ability to ask these questions, remains a singular, precious phenomenon in this moment for us. And what of the other levels of the multiverse? The endless cosmic bubbles, the quantum splits, the mathematical realities. These push the boundaries of proof even further. How do we glimpse a level 2 bubble universe, spawned from eternal inflation, with its own distinct physical laws? Our current physics tells us these are beyond our causal horizon, unreachable even in principle. How do we interact with the infinite branches of a level 3 quantum multiverse, where every decision, every random quantum fluctuation births a new reality? By definition, these realities are non-interacting, forever separated. This is where the scientific method, as we traditionally understand it, stretches to its very limits. We seek evidence, testability, falsifiability, and for many of these multiverse scenarios, direct empirical evidence remains stubbornly out of reach, yet the pursuit is not futile. Far from it. It pushes us to refine our theoretical frameworks, to search for subtle, indirect clues. Are there faint gravitational ripples from a colliding brain in higher dimensions, as string theory might suggest? Could we detect an imprint, a bruise, on the cosmic microwave background, left by a brush with another bubble universe? These are the tantalizing questions driving the next generation of observatories and particle accelerators. The quest for infinity, then, becomes a journey not just of observation, but of profound conceptual exploration. When direct observation falters, when our instruments reach their absolute limits, that's when the human mind, armed with mathematics, logic, and imagination, truly takes flight. This is the domain of theoretical physics, where elegant equations and bold hypotheses become our telescopes into the unseen. String theory, loop quantum gravity, the holographic principle. These aren't just abstract ideas. They are our attempts to build a coherent, comprehensive map of reality, even if that reality extends far beyond our immediate perception. Consider the sheer audacity of these theories, my friends. They propose extra dimensions curled up smaller than an atom, or space-time itself woven from discrete loops, or even the entire universe as a projection from a lower dimensional boundary. These are not easy concepts to grasp, but they represent humanity's relentless drive to understand the fundamental nature of existence, to unify the disparate pieces of our cosmic puzzle. And often, these theories, in their pursuit of unification, find themselves naturally accommodating the concept of infinity, or at least a universe far grander and more complex than our simple 3 spatial dimensions could ever contain. The beauty of this scientific journey is that every answer we uncover inevitably leads to more questions. We discover the CMB, and suddenly we're asking about inflation. We confirm a flat universe, and suddenly we're grappling with infinite copies of ourselves. We develop quantum mechanics, and suddenly we're contemplating an infinite branching of realities. The frontier of knowledge is not a fixed line we will one day cross, but an ever-expanding horizon that recedes as we approach it, revealing even grander vistas. And this, I believe, is the true spirit of quote 56. It's not about definitive answers handed down from on high, but about the process of asking, of exploring, of pushing the boundaries of what we thought possible. It's about nurturing that insatiable curiosity that lies within each of us, that innate desire to understand our place in the cosmos. We are, after all, creatures of the universe, made of stardust, imbued with the capacity to reflect upon our own origins and destiny. The search for infinity is a humbling experience. It reminds us of our own smallness in the face of such immeasurable grandeur. Yet, it is also incredibly empowering. The fact that our finite minds can even conceive of infinity, can develop mathematical frameworks to describe it, can build instruments to search for its echoes, is a testament to the extraordinary power of human intellect and imagination. We may never definitively prove that the universe is infinite in every conceivable way, but the quest itself enriches us, expands our consciousness, and deepens our appreciation for the bewildering beauty of existence. So, as we bring this particular chapter to a close, let's carry forward this sense of wonder. Let's embrace the mystery, the unanswered questions, and the profound implications of what we do know. The universe, whether truly infinite or merely unimaginably vast, is a place of boundless marvel. And our journey to understand it, my friends, is only just beginning. We are the curious minds, the fellow stargazers, forever reaching for the stars, forever pondering the ultimate nature of everything. And that in itself is an infinite and beautiful pursuit. And so, my friends, we arrive at a profound juncture, don't we? We've journeyed through the cosmic light bubble of our observable universe, peered into the geometry of space-time, and even dared to glimpse the speculative realms of the multiverse. We've wrestled with the very fabric of reality, from the Big Bang to the Big Bounce, from strings to loops, from the holographic principle to the quantum foam. And yet, after all this, we find ourselves standing on the precipice of a truth both humbling and exhilarating. Absolute definitive proof of an infinite universe remains tantalizingly beyond our grasp. It's a methodological challenge, isn't it? How do you prove something is endless when your own existence is finite? When your instruments have limits, and when the very speed of light dictates how far and how deep we can ever truly see? It's like trying to weigh the ocean with a teacup. or measure the wind with a ruler. Our observable universe, vast beyond imagining, is still but a finite bubble within what might be an infinitely larger whole. We can gather compelling evidence, build elegant theories, and make incredibly strong inferences, and indeed, the flatness of our universe is a powerful indicator. But the final, undeniable proof of spatial infinity, of a universe that simply never ends, seems to evade our direct verification. So if absolute proof is elusive, why do we persist? Why do we, the curious minds and fellow stargazers gathered here on Dreamy Science, continue to ask this monumental question, to push the boundaries of our understanding, to chase after an answer that might forever remain just beyond the horizon? This is where the true journey begins, isn't it? This is where science transcends mere data collection and measurement, where it intertwines with philosophy, with poetry, with the very essence of what it means to be human. We ask because we must. We ask because the question of infinity, whether spatial or temporal, touches upon the deepest chords of our existence, our significance, our place in the grand cosmic tapestry. Consider the philosophical implications, my friends. If the universe is truly infinite, what does that mean for our unique existence? If level 1 of the multiverse hypothesis holds, if there are infinite cosmic horizons out there, then somewhere, infinitely far away, there are infinite copies of you, reading this, experiencing this moment, perhaps even making slightly different choices. Every conceivable event, every possible configuration of matter and energy must occur an infinite number of times. It's a dizzying thought, isn't it? Does it diminish our individual uniqueness, or does it elevate the sheer, mind-boggling possibility of existence itself? For some, the idea of infinite copies can feel disquieting, a reduction of the preciousness of our singular lives. But for others, it's an expansion of wonder, a testament to the inexhaustible creativity of the cosmos. It suggests that every choice we make, every breath we take, isn't just a fleeting moment but a ripple in an infinite ocean of possibilities, played out again and again across the boundless expanse. Our story, our unique story, is simultaneously one of countless variations and yet, in this instance, utterly singular and precious. And what of meaning? Does an infinite universe render our endeavours meaningless, a tiny flicker in an endless void? Or does it paradoxically imbue our finite moments with an even greater significance, knowing that even in the face of the boundless, we strive, we create, we love, we understand? I believe it's the latter. Our capacity to even contemplate infinity, to grapple with concepts that stretch the very limits of our imagination, is a testament to the extraordinary power of the human mind. We are finite beings reaching for the infinite, and in that reach, we define ourselves. The quest for infinity also profoundly challenges our perception of reality itself. If the universe is infinite, then what we perceive, what our senses tell us, what our most powerful telescopes reveal, is merely a fraction of the whole. It means there are realities beyond our current comprehension, phenomena we can't yet detect, laws of physics that might subtly shift across vast, unimaginable distances. It teaches us humility, reminding us that our current understanding, however advanced, is always provisional, always a stepping stone to a deeper, more encompassing truth. The universe isn't just bigger than we think, it might be stranger than we can imagine. This brings us to the very limits of knowledge. Is infinity something we can ever truly know in a complete sense? Or is it a concept we can only ever asymptotically approach? Perhaps some questions are designed not to be definitively answered, but to be perpetually explored. The act of asking, of seeking, of pushing against the boundaries of what is known is itself the purpose. It's the engine of scientific discovery, the fuel for philosophical discourse, and the wellspring of artistic inspiration. The universe, in its potential infinitude, becomes a grand, eternal puzzle, inviting us to forever piece together its mysteries. And the scientific quest, my friends, is far from over. While definitive proof of infinity might remain elusive, our tools and techniques are constantly evolving. We're not just reiterating old questions, we're refining them, adding new layers of data and theoretical frameworks. Think about the next generation of observatories, peering further back in time, mapping the CMB with even greater precision. Gravitational wave astronomy is opening a new window onto the universe, allowing us to hear the cosmos in ways never before possible, potentially revealing structures and events that light alone cannot betray. The study of dark energy, that mysterious force accelerating the universe's expansion, continues to be a frontier, with implications for the ultimate fate and geometry of the cosmos. Each new piece of information, each new theoretical insight, helps us paint a more detailed picture, nudging us closer to understanding the true nature of the universe's extent. Perhaps we will find subtle deviations in the CMB that hint at a finite yet incredibly vast universe. Perhaps new cosmological models will emerge that offer a different perspective on how we define infinite. Or perhaps, with future breakthroughs in quantum gravity, we will finally reconcile the disparate realms of the very small and the very large, unlocking a unified theory that inherently defines the universe's ultimate scale, or lack thereof. The point is, the quest continues, propelled by that insatiable human curiosity. Ultimately, the beauty of this question, quote 60, lies not just in a potential answer, but in the journey itself. It is a journey that expands our minds, broadens our horizons, and deepens our appreciation for the cosmos. It forces us to confront our own limitations, to embrace the unknown, and to marvel at the sheer scale of existence. It instills a profound sense of awe and humility, reminding us that we are but a small, conscious part of something unimaginably grand. In the face of such immensity, our shared exploration becomes a beacon. We, the curious minds, the fellow stargazers, are united in this pursuit of knowledge, this shared wonder. We may never definitively prove infinity, but in the act of asking, of seeking, of dreaming, we touch upon it conceptually. We expand our capacity for understanding, for imagination, for profound contemplation. And that, my friends, is a truly infinite and beautiful pursuit in itself. The universe, whether finite or infinite, calls to us, and we, with our boundless curiosity, answer. And the conversation, the exploration, the dreamy science continues. We've journeyed far, haven't we, my friends? From the edges of our observable bubble, a cosmic light sphere 93 billion light-years across, to the mind-bending realms of the multiverse, where other realities might shimmer just beyond our grasp. We've plunged into the fiery crucible of the Big Bang, seeking whispers of a cyclical Big Bounce, and grappled with the profound implications of a theory of everything, where the universe's fundamental truths might finally coalesce. We've peered into the cosmic looking glass, seeking answers to the most fundamental question: is the universe actually infinite? And as we stand here, at the precipice of our understanding, a new vista unfolds, not just of scientific inquiry, but of profound philosophical contemplation. The data, the theories, the intricate mathematics, they all point towards a compelling possibility that our universe, in its grandest scale, might indeed be spatially infinite. But what does that actually mean for us, for you and me, for our individual lives flickering within this boundless expanse? If space stretches forever and the laws of physics remain consistent throughout, then the sheer statistical probability dictates that everything must repeat, not just once, but infinitely many times. Somewhere, out there, in a region of space so unimaginably distant that the numbers lose all meaning, there's another Earth, another you, another me, perhaps having this very same conversation down to the last quantum fluctuation. It's a thought that can be simultaneously exhilarating and deeply unsettling, isn't it? Does this possibility of infinite copies diminish our uniqueness, making us feel like mere echoes in a cosmic hall of mirrors? Or does it, paradoxically, elevate the preciousness of this specific moment, this particular consciousness, this unique journey we are living? I believe it does the latter, for even if infinite versions of us exist, this experience, this stream of consciousness, this breath, is singular. It's our personal window into the infinite, our unique dance with reality. The vastness doesn't erase our significance, it frames it, making our brief incandescent existence against the backdrop of eternity all the more poignant and miraculous. Our finite lives, our finite choices, become infinitely valuable, precisely because they are ours, here and now in this particular unfolding of cosmic history. Yet, despite the compelling theoretical arguments and the elegant simplicity of a flat universe, we must confront the humbling truth. Our perception is finite. We are forever bound by the speed of light, by the age of the universe, by the very fabric of space-time that dictates what information can reach us. Our observable universe, that magnificent bubble of light and galaxies, is our cosmic horizon, our lighthouse in an ocean whose true expanse remains veiled. We can infer, we can hypothesize, we can build sophisticated models, but we cannot, at least not yet, directly observe the universe in its entirety. It's like standing on a vast flat plain and trying to deduce its infinitude from the curvature of the horizon. Our instruments tell us it looks flat. But does it go on forever? That leap from observation to extrapolation is where science meets the sublime, where the known gives way to the unknowable in its immediate sense. It demands a certain epistemological humility, an acknowledgement of the limits of even our most powerful telescopes and brilliant minds. This is where the grand tapestry of theoretical physics truly comes alive, where human ingenuity stretches beyond the limits of current observation. Concepts like string theory, with its hidden dimensions and vibrating fundamental strings, or loop quantum gravity, which posits a granular quantized space-time, aren't just arcane mathematical exercises. They are profound attempts to build a coherent picture of reality at its most fundamental level, frameworks that inherently grapple with the very nature of space, time, and potential infinitude. They offer tantalizing glimpses into what lies beyond our current comprehension, suggesting that our everyday 3 dimensions of space and one of time might be but a small slice of a much richer, multi-dimensional reality. These theories don't just describe what is, they explore what could be, pushing the very boundaries of our cosmic imagination. They are our intellectual vessels for navigating the uncharted waters of the truly infinite. And then there's the truly mind-bending holographic principle, a concept that challenges our very understanding of what space and information are. Imagine, if you will, that all the information contained within a three-dimensional volume of space, including every star, every galaxy, every particle, every conscious thought, could be entirely encoded on a two-dimensional surface, a cosmic hologram, if you will, at its boundary. If this is true, what does it mean for the volume of the universe, for its inside and outside? Does infinity then become a question of infinite information density on a finite boundary, or an infinite boundary containing infinite information? It fundamentally redefines the canvas upon which we paint our understanding of existence, blurring the lines between what is real and what is information, and opening up entirely new avenues for conceptualizing infinity. It's a profound shift in perspective, suggesting that our perceived reality might be a projection, a grand illusion that nonetheless contains the complete story of existence. Let's revisit the multiverse, not just as a scientific hypothesis, but as a profound philosophical challenge. If level 2 multiverses exist, those bubble universes born from eternal inflation, each with its own unique set of physical laws, then our universe's remarkable fine-tuning for life, the precise values of fundamental constants that allow stars to burn and atoms to form, becomes less a miracle and more a statistical certainty. We simply inhabit one of the universes where the dice roll just right for consciousness to emerge. Does this make our existence less special? Or does it deepen our appreciation for the sheer improbable luck of being in this particular, life-friendly bubble among an infinite sea of barren, lifeless realities? It shifts the question from why us to why this universe, and, in doing so, deepens the wonder of our specific cosmic address. And then there's the many worlds interpretation, level 3 of the multiverse. Here, every quantum event, every choice we make, every toss of a coin causes the universe to split into diverging, non-interacting realities. Every possibility actually happens somewhere. This isn't just an infinite space, it's an infinite personal history, an endless branching tree of yous living out every conceivable permutation of your life. Imagine that. A version of you who chose differently this morning, a version who pursued a different career, a version who never even existed in this reality. It's an infinity woven into the very fabric of our decisions, an ever-unfolding cascade of possibilities that makes our individual conscious journey here and now all the more precious, a specific path chosen from an infinite array. It's a dizzying thought, a cosmic, choose-your-own-adventure that plays out in countless parallel universes, making this path, this story, this unique sequence of events, uniquely ours in the most profound sense. So, why do we embark on this relentless quest, my friends? Why do we strain our minds against the incomprehensible, building ever larger telescopes and ever more complex theories, even when definitive answers seem to recede into the cosmic mist? It's more than just scientific curiosity. It's a fundamental human drive. It's the inherent desire to understand our place in the cosmos, to map the boundaries of our existence, to find meaning in the vast, silent expanse. This quest for infinity isn't just about the universe out there, It's about the universe within us, the boundless capacity of the human mind to imagine, to question, to aspire to knowledge that transcends our immediate reality. It's the ultimate act of intellectual exploration, a testament to our spirit of inquiry, a defiant reaching out into the unknown that defines us as conscious beings. We are, in essence, trying to understand the nature of our own consciousness by understanding the nature of everything else. What does the next chapter of this grand scientific odyssey hold? We are constantly pushing the boundaries of what's observable. Future gravitational wave detectors, like the proposed Laser Interferometer Space Antenna, LISA, promise to peer even further back in time than the CMB, potentially detecting ripples from the very first moments of the Big Bang, perhaps even signals from a universe before our own, if the Big Bounce theory holds true. On the quantum front, physicists are designing ever more sensitive experiments to probe the nature of space-time at its smallest scales, hoping to find the elusive quanta of gravity that might unlock the secrets of a unified theory. And the burgeoning field of AI, coupled with vast cosmological datasets, might uncover subtle patterns, anomalies, or statistical correlations that hint at larger unseen structures or interactions with other universes. We are only just beginning to learn how to ask the right questions, to build the right instruments, and to interpret the right data that might one day offer a clearer glimpse into the true extent of reality. But perhaps the universe's greatest gift, its most profound lesson, is that it retains its mystery. True infinity in all its mind-bending glory might be something our finite minds can never fully grasp, only approach, marvel at, and contemplate. It keeps us humble, reminding us of the limits of our knowledge, yet simultaneously inspires us to reach further, to dream bigger. The beauty isn't necessarily in finding a definitive yes or no to the question of infinity, but in the quest itself, the journey of discovery, the expansion of our understanding, the profound sense of wonder that washes over us when we truly contemplate the cosmos. This is the essence of dreamy science, isn't it? To blend the rigour of scientific inquiry with the boundless expanse of imagination, to find the poetry in the physics, the awe in the astrophysics, and to understand that the greatest truths often lie at the intersection of what we can measure and what we can only imagine. We began this journey by asking if the universe is infinite. We end it, not necessarily with a simple answer, but with a transformed understanding of the question itself. We've seen how the universe's geometry, the dance of light and expansion, the tantalizing hints of other realities, and the very fabric of space-time itself, all whisper of possibilities that stretch beyond our immediate grasp. Whether our universe is truly infinite in space and time, or merely finite yet unbounded, like the surface of a sphere, it challenges our deepest notions of individuality, purpose, and reality. It compels us to look inward as much as outward, to ponder the nature of consciousness that can even ask such questions, to understand that the universe is not just out there, but also profoundly within us. The cosmos, my friends, is a boundless mystery, a canvas of endless wonder. It is a place where the most rigorous science meets the most profound philosophy, where data points to the sublime, and where every answer only begets 1,000 new questions. So, as we conclude this particular chapter of our cosmic exploration, I invite you to carry this sense of wonder with you, to continue gazing at the stars, and to keep asking the big questions. For in that continuous quest, in that relentless pursuit of understanding, we truly connect with the infinite spirit of the universe itself. What do you think, my friends? Is the universe infinite? The journey to find out is far from over, and it is a journey we take together.